Did you know that in 1966, the Luna 9 mission of the Soviet Union achieved a historic milestone by becoming the first spacecraft to successfully reach the surface of the Moon and execute a soft landing? Prior to this, we had primarily been sending objects hurtling toward the Moon with the hope that they might crash into it and transmit some data if we were lucky. Additionally, did you know that the Soviets also achieved an early lunar mission milestone in 1959 when their Luna 2 spacecraft became the first human-made object to impact the Moon or any other celestial body beyond Earth? You might also be aware that in August 2023, Russia attempted another soft lunar landing with Luna 25, but unfortunately the mission failed, resulting in the spacecraft crashing into the lunar surface, leaving behind a new crater and more human-made debris. This might seem like a significant regression in lunar landing capabilities over time, despite technological advancements. One could wonder if there's a problem with Russia's lunar exploration efforts. However, it's worth noting that other nations like Japan with its iSpace mission in 2023 and India's Chandrayaan-2 mission a couple of years earlier also experienced lunar landing failures. Japan is known for its advanced technology and manufacturing, and India boasts some of the brightest engineers in the world. So, why is lunar landing so challenging? One lesser-known factor is the Moon's peculiar and uneven gravitational field. Unlike Earth, which has a consistent gravitational force around its perimeter, the Moon's gravitational force varies from one region to another, creating an uneven, lumpy gravitational field. Some areas on the Moon, particularly impact basins, exhibit unexpectedly strong gravitational fields due to the accumulation of mass from past asteroid impacts. In 2019, scientists confirmed the existence of a mysterious mass beneath the Moon's south pole, estimated to be equivalent to around 2 quadrillion tons. While it's unlikely to be an ancient alien mothership, the true nature of this mass remains a mystery. More plausibly, it's located beneath the South Pole Aitken Basin, a massive oval-shaped impact crater on the Moon's far side formed around 4 billion years ago. The Moon bears visible scars from countless large impacts over its history, which have likely scattered mass concentrations in unpredictable locations, resulting in the Moon's erratic and unpredictable gravitational forces. This variability can pose challenges for spacecraft attempting to land on the Moon. The history of lunar landing attempts reveals a pattern of failure, especially in the early days of lunar exploration during the late 1950s and early 1960s. During this period, successful landings were rare. However, this should not be surprising given the technical and scientific challenges involved. As we delve deeper into lunar exploration history, we discover that many early missions faced difficulties in achieving their lunar landing objectives. Despite high expectations, NASA's Surveyor program in 1966, which aimed to lay the foundation for the Apollo missions through robotic moon landings, faced significant challenges. The success rate of these missions did not instill much confidence. Out of the 7 Surveyor missions, one lost control midway and crash-landed on the Moon, while another lost radio contact with Earth just 2 minutes before its landing attempt, leaving us in the dark about its fate. When we shift our focus to the Apollo program, we see a stark contrast. No human landing on the Moon resulted in failure. This contrast highlights one key reason for the failure of many moon landings: the ability of humans to adapt and solve problems on the spot, which robots couldn't do, at least during that era. For instance, the first Apollo 11 moon landing would have ended in failure if not for Neil Armstrong's exceptional piloting skills. The lunar module, named Eagle, encountered deviations from its planned trajectory as it separated from the main spacecraft, and the computer guidance system couldn't adjust for unexpected variables. In a crucial moment, Neil Armstrong chose to trust his instincts over the computer, skillfully landing on the Moon manually with just seconds of rocket fuel left. However, relying on a veteran Navy pilot like Armstrong to troubleshoot in real time isn't a feasible option for every moon landing mission. Robotic missions require everything to go perfectly according to the plan, as they lack the ability to adapt. This means that any deviation or unforeseen issue can quickly turn a mission into a failure. The Moon's proximity to Earth might make it seem like a manageable destination, but it's just far enough that remote control is impractical. The average round-trip communication delay is about 2.5 seconds, which is insufficient for precise control during a moon landing. It's worth noting that NASA has achieved successful landings on Mars in recent decades despite the greater distance. Mars, with its minimal and thin atmosphere, presents its own set of challenges, but the presence of an atmosphere does aid in the landing process. This underscores why landing on the Moon, lacking any atmosphere to assist, remains an intricate and challenging endeavor, but it's considerably denser than what we encountered on the Moon. This means you can utilize a parachute on Mars with great effect. This is the game changer. A parachute alone can't ensure a soft touchdown on Mars, but it can significantly reduce the spacecraft's velocity and give the lander enough time for a controlled descent. For the final touchdown phase, something as simple as airbags can be used to cushion the impact of a lighter payload. In contrast, larger NASA rovers have relied on a combination of retro rockets and a sky crane to safely deliver the payload to the surface due to the Moon's lack of atmosphere. Achieving a fully propulsive landing on the Moon is exceedingly challenging, even for the SpaceX Falcon 9, which now makes rocket-powered landings seem routine. This booster heavily depends on Earth's atmosphere for controlled descent via aerodynamic drag and grid fins. Controlled descent via aerodynamic drag and grid fins. These lunar landers face the daunting task of transitioning from orbital velocity to zero velocity relative to the Moon's surface, relying solely on a meticulously timed series of rocket burns. This is a significant challenge no matter who you are. We should also acknowledge the added complexity of the landing location on the Moon in modern missions. In the past, moon landers would take the path of least resistance. For instance, the first Luna 2 impact followed a nearly ballistic trajectory. The Soviets directed their probe straight at the center of the Moon's visible side, hitting it dead center on the east-west axis, about 30 degrees north of center. With more controlled landings like Apollo, we targeted areas near the equator on the visible side of the Moon. This approach allowed the spacecraft to follow a relatively two-dimensional path, launching from the equator region of Earth and heading straight out to the equator region of the Moon and back, as flat as possible. China broke this cycle by achieving a soft landing on the far side of the Moon with Chang'e 4 in 2019. However, recent lunar excursions like the unsuccessful I-Pace and Luna 25 landers have been targeting the Moon's south pole. This region holds great importance for future human exploration, as we believe it contains substantial stores of water ice. This resource is crucial for more than just drinking, as water provides oxygen for breathing and hydrogen for fuel. This also means we need to figure out how to insert our spacecraft into a polar orbit around the Moon, requiring a more three-dimensional flight path. Landing at the south pole of the Moon isn't impossible, as proven by the Indian Space Agency's success with their Chandrayaan-2 mission. India's advantage was learning from their initial failure with Chandrayaan-2. Most would agree that there's no better way to improve at something than by attempting it, failing, and then learning from your mistakes. This holds true for most endeavors, except perhaps free solo mountain climbing, where mistakes can be fatal. When it comes to sending robots to the Moon, as long as there's funding for the mission, we can keep sending them into space and learning along the way. As mentioned earlier, NASA faced numerous failures before achieving success. Out of the 9 Project Ranger missions from 1961 to 1965 that aimed for a soft moon landing, only the last 3 succeeded. The 7 Surveyor missions saw 5 successful touchdowns, and all 6 Apollo missions that reached the Moon without any mid-course failures executed flawless landings. Now, in the 21st century race to the South Pole of the Moon, we're seeing a similar pattern. Despite the incredible advancements in computer technology, transistors, and microchips, we sometimes have to face failure before achieving success. We need to learn to walk before we can run. Join us here every week for the latest updates on everything related to the aerospace industry and interstellar exploration. If you enjoyed this video, please give it a thumbs up. It truly makes a difference. We release one long-form essay and one news update every week,